Okay, in this short video, I'm just going to go ahead and explain what you have to do in the DSP project number 5. It is pretty self-explanatory, but I'm just going to go ahead and go over different steps to make them clear in case if you read it and then it's not clear to you. So in this project, basically, you are creating FIR filters, the one that were studied in chapter number 7, low pass, high pass, and band stop using the Fourier Transform methods. The equations are there that we discussed in chapter number 7. And once you create those filters, then you will treat them with one of the window functions. And the objective is to, of course, design the filters and to plot the response of the filter for both without using the window function and with the window function. So the first thing that you'll have to do, of course, you're going to go ahead and ask the information about the filter from the user as what is the length of the filter. Remember, length of the filter has to be an odd number. And from that length, you can calculate the value of m, because the length goes from -m to m. And the length, of course, is 2m plus 1. So if it is 15, then m is going to be 7. So it's going to go from -7 to 7. If it is 16, m is going to be, sorry, it cannot be 16 because it has to be odd. If it is 17, then of course, m is going to be 8. And it's going to go from -8 to 8. So first, you're going to design the filter from -m to m, and then of course you are going to move it to make it causal. First, you're going to design the non-causal filter and then the causal filter. Remember, the equations that are given that we discussed, they are for non-causal filter. However, remember, as we discussed, that the coefficients of the causal and non-causal, they're not going to change anyways. So it's going to be the same coefficients only when you are writing the transfer function of the filter down. Then, of course, the causal transfer function is going to be different from the non-causal transfer function. So you're going to ask user, what is the length of the filter? You're going to ask user, what is the filter type? Low pass, high pass, band pass, or band stop. And then, of course, you need the sampling frequency to plot the response, because for the response, of course, in the equation, you do need the sampling frequency. And then you're going to ask what type of window needed to be used in order to treat the filter. Now, once user is going to give you these 4 pieces of information, then you can either use a switch function or an if-else loop to select whichever user has given you. So if he's giving you low pass, you're gonna, you are writing down the equations from chapter 7 for low pass, high pass, band pass, and band stop. Then whichever user is giving you, you can either use the if or switch condition to select that specific filter and use the equation of the filter from the given information. That is, first of all, fs. And then if the user is going to give you the low pass and high pass, of course, you need the cutoff frequency. So you're going to ask user again, what is the cutoff frequency? And user is going to provide you that information. And based on those pieces of information and the length of the filter, you are going to create the filter. That is, you're going to calculate the coefficients of the non-causal filter. All right, once you do that, then you're going to go ahead and calculate the frequency response of that filter. Yeah, now you can use either the freq function and use 1024 points, or you can actually freq function is going to be the one that you're going to be using, because of course, if it's a long filter, you cannot really write down the equation and convert z into e to the power j omega like we do manually. So just use the freq function that you used in the previous project and calculate the response of the filter. And remember, in freq, you have simply the coefficient of the numerator and coefficient of the denominator and the number of points that you want. In this case, I'm asking you to use 1024 point. and that's going to produce the response of the filter and the value, the points for omega between 0 and pi, and those will be 1024 points. And for each point, the value of the transfer function is going to be calculated. And of course, your B are the coefficients of the filter that you calculated using those equations. And A is going to be 1 because it's a FIR filter. So the denominator is going to be 1. Okay, now once you plot the response, of course, amplitude response of this, then you are going to treat the filter using one of the window functions that we discussed again in the text. And you're going to ask, well, you already asked user basically that which window function is required right over here in part number D. So again, you can use an if statement or a switch statement to choose that specific window function and then calculate the coefficients of that window function. Then multiply the coefficients by the coefficients of your, and remember the coefficients that you're calculating are going to be from -m to m. And you're going to use the coefficients of the window function, multiply them with the coefficients of your non-causal filter that you have calculated. And that will be your treated coefficient of the treated filter, the non-causal. But again, the coefficients are same for causal and non-causal, only the transfer function is different. So once you have the coefficient of the treated filter, again, you're going to do the same thing. That is, you are going to plot the frequency response of that using the freq function. Use 1024 point between 0 and pi. And once again, calculate the amplitude response of that and then plot that as well. Now make sure when you're plotting the frequency response, you need to plot versus frequency. So convert the omega into f, the normalized frequency in radians into the frequency in hertz. Again, we discussed that in chapter number 7 and chapter number 6 both. For the bandpass and bandstop filter, you have to ask user, as it is given in number 5. If users select bandstop and bandpass, ask for the lower and upper cutoff frequency. So if user selects bandstop and bandpass, then you have to ask what is the lower cutoff frequency and what is the upper cutoff frequency, because it has both lower and upper cutoff frequency, omega low and omega upper. And you're going to ask, of course, in terms of f low and f upper. But for the high pass and low pass, it's only a single cutoff frequency. So this is pretty much the project. And some samples are given to you. So for this one, I chose 99, length is 99. And I chose low pass filter, I chose Hamming window. And my sampling frequency was 8,000 hertz, and my cutoff frequency was 2,000 hertz. So this is the original filter response, causal filter. You can see all the Gibbs oscillation in the stop band and pass band. And once I treated that using Hamming window, then it became pretty smooth in the pass band and the stop band. However, the transition band became a little bit wider, which is the penalty of using the window function. But overall, the pass band is, solidly smooth. So some of the responses are given, and this is a phase response. So it seems like you're plotting both magnitude response and phase response. So plot both of them basically, and I'm using subplots. And so go ahead and use subplots for one for the magnitude response and one for the phase response. Here's an example of bandpass filter. Blackman window function is used. Length is 19. 20 kilohertz is the sampling rate. Lower cutoff frequency is 5 kilohertz, and upper cutoff frequency is 7 kilohertz. Remember, the complete response is between 0 to fs by 2, the folding frequency. So if your sampling frequency is 20 kilohertz, then your folding frequency is 10 kilohertz. That means both of these cutoff, the lower cutoff and upper cutoff, must be between 0 and 10 kilohertz. So keep that in mind. Do not take, if you're taking sampling frequency to be 20 or 30, do not go close, do not go beyond half of that and choose a frequency, cutoff frequency, beyond half of the sampling frequency, because that is not going to, it's going to become undersampled in that case. So make sure that you go between 0 and half of the sampling frequency and choose all of your cutoff frequency in that range. So again, this is the response of the filter without window function, and this is with the window function and the phase response. So this is the project. As I said, even if you read it, it is going to make sense. But I hope this short video is going to further help you in understanding what exactly you are trying to do in this project.